Good afternoon, those folks in the room and everybody online. Welcome back to Earth Talks, colloquium series on urban system science, sponsored in part by the Earth and Environmental Systems Institute and held jointly with Johns Hopkins and Morgan State Universities. And hopefully some of those folks are joined us on Zoom. We have passed the halfway mark for the semester. It's after spring break, though we'll be out of phase with our Hopkins and Morgan State colleagues on spring break. Sorry about that. And we've had a wide range of interesting topics. Today's topic is close to the heart of our atmospheric science research efforts. And I'm honored to introduce Dr. Let me see if I can pronounce this close to right. Tirthankar?
That's right.
Good. Tirthankar Chakraborty goes by TC, an earth scientist at Pacific Northwest National Lab in Richland, Washington. Richland, correct? Yep. Yes, okay. TC earned a PhD from Yale University, where he studied the Earth's surface energy balance and aerosol climate interactions. He's currently working to improve representation of the urban system in land models that are within climate models, and is studying extreme weather events over coastal cities. He recently received both a DOE early career grant to improve urban representation in climate models and a NASA interdisciplinary science grant studying disparities in heat exposure in US cities. And today he's going to talk to us about spatial variability in urban microclimate. So let's welcome TC.
Thanks for the introduction, Ken. Hello, everyone, both in person and online. So I'll be talking about modeling spatial variability of urban microclimate. So this is kind of the presentation overview. I'm going to be talking about some background of the topic itself, some of the current research gaps in our understanding and ability to model urban microclimate and its spatial heterogeneity, and then some potential paths forward. And this would include some preliminary results from some of the work we are currently doing. Starting with the background, so the physical process of urbanization is the replacement of natural land surfaces with built-up structures. This includes parking lots, buildings, streets, roads, etc. And you can see examples here for Las Vegas of the built-up area increasing over time from multiple satellite imagery. But broadly, urbanization is the change in natural land cover, which can be due to any kind of urban planning. For instance, changes in urban green space or transition from native to non-native vegetation. For instance, if you are in an arid region which does not support a lot of trees, you could, in theory, have a lot more vegetation due to irrigation, and that's really part of the urban development. So there has been rapid urban expansion over time. And you can see that in the country level increase in built-up area from 1992 to 2020, as well as the increase in the urban extent for multiple large cities all over the world. And this urban expansion has impacts on weather and climate, but it's not just urban expansion. So you have actually the change in the urban extent, which is the urban expansion. You have changes in urban surface properties. This includes changes in urban vegetation. This includes changes in the actual thermal properties of urban areas, such as how much radiation is reflecting back into space, also called the albedo, or what is the amount of radiation emitted by urban surfaces compared to a black body, also the emissivity, etc. Then you have anthropogenic activities where you have adding energy into the urban system. And all of this has impacts on weather and climate. There are many different ways urbanization affects weather and climate. The big ones, or probably the most common ones that we hear about, are the urban heat island effect, where temperatures are locally warmer than the surroundings, as well as the urban dry island effect, where you have less relative humidity in urban areas compared to their surroundings. Urbanization also affects cloud formation and precipitation, usually over and downwind of cities, and also changes air pollution. This urban growth and densification may also lead to broader feedback to the atmosphere. So not just changes in surface properties, but also changes in the atmospheric systems. And part of that is covered in the cloud and precipitation aspect. Now, in addition to the overall urban impact on climate, urban areas can be very heterogeneous. And you can see here these are all Google Earth imagery for over New York. And these are different parts of New York. And you can see very different materials, very different morphology, and very different amounts of urban vegetation. And all of this variability affects local microclimate. An example here is shown for the surface urban heat island intensity, which is the local increase in temperature compared to this background climate based on satellite observations. And this is for New York, and you can see large spatial variability over different parts of the city. And this urban heterogeneity matters because it impacts who is exposed to heat within urban areas. And not just heat, but also other climate risks. An example here is shown for over 175 cities in the US, where this urban heterogeneity leads to this intra-urban temperature variability, which can then have covariance with population distributions. Incidentally, for the US, this means that in over 90% of the cases, you have higher potential for heat exposure in poorer and more non-white neighborhoods. However, there are a lot of issues with how to deal with this heterogeneity in urban areas, both from the observational perspective as well as the modeling perspective. The first big issue relates to the observations. I talked about a lot of satellite-derived estimates of either surface urban heat island or the land surface temperature. These are not equivalent to human experiences of heat. When we are talking about heat, traditionally we are talking about weather station measurements of the ambient air temperature, usually 1.5 to 2 meters above the ground. And these are extremely rare in urban areas. We don't really set up standard weather stations in urban areas. That's why the urban climate literature has a lot of studies using satellite-derived surface temperature. But these are not the same. And on the ground-based sensor side, you have certain advantages. It's giving you something which is relevant to human exposure of heat. It's also available for all skies, so cloudy skies and clear skies. And they're generally cheaper to calibrate and fix locally compared to like having a sensor up on a satellite. The advantages of satellite observations relate to the spatial heterogeneity that it can capture, because you're essentially getting continuous measurements of the urban surface and getting some estimate of the thermal signal from the urban surface. They also generally use identical sensors, so you don't have to deal with like different quality control for different kinds of sensors or drifts in weather station measurements and so on. The disadvantages include that they're mainly available for, only available for clear sky conditions. There are a lot of impacts of view angle of the satellite on what it's exactly measuring. And most importantly, it's not really measuring air temperature. It's measuring the temperature of the surface. And this is not something we directly feel because we are not touching the surface with our bare skin. And it's the difference between, say, hovering your hand over a boiling pot versus touching it directly. It's not the same amount of heat. And because of this, it's not really ideal to use surface temperature to look at spatial variability in urban areas. We wanted to test this in a previous study where we used citizen weather stations over Europe. So we had over 50,000 weather stations from this French company called Netatmo, where people basically buy these stations, put them either outdoors or indoors, but you only get access to the outdoor sensors through their API. And we looked at the July 2019 heat wave period and tried to understand the urban warming and drying effect. We looked at many different things, but the one I want to focus on right now is this intra-urban variability in potential heat exposure. So what we did, we took the satellite-derived land surface temperature and created these decile regions. So basically, within each urban area, the pixels from the 90th to 100th percentile of LST, land surface temperature, is in the 10th decile region. Similarly, the 80th to 90th percentile is in the 9th decile region, and so on. So basically, from the background to the 10th decile, you're getting increasingly warmer parts of the city. And then we chose the weather stations within each of the decile region and tried to understand what is the spatial variability of skin temperature or surface temperature, air temperature, relative humidity, and the heat index. So the heat index is a combined metric of temperature and humidity and how humans might respond to it under shaded conditions. So what we find is that surface temperature, as expected, increases with the decile regions. Note that these values are corresponding to the sensor locations. So they're not the average of the decile pixels. So this basically shows that the sensor locations are more or less representative of the overall distribution of the temperature within the city. Air temperature also shows an increase, but the magnitude of increase is much lower, like 1/10 or something. Relative humidity shows an anti-correlation. So the warmest part of the city shows lower relative humidity than and the coolest parts of the city show the highest relative humidity. So this compensating effect of temperature and humidity means that heat index actually shows very little variability within urban areas. Now, we wanted to know what this means for the disparities we saw based on the surface urban heat island earlier. The problem is that we cannot really use these crowdsourced data to understand disparities. Part of the reason has to do with there are a lot of uncertainties in the crowdsourced data. The big one relates to the lack of metadata in the citizen weather station measurements, where people will put it in their backyard, but not really in shade, which affects the measurements. So we did some calibration against kind of the research grade sensor networks. And what we found was you're overestimating the sensible some temperature and underestimating relative humidity, which is what we would expect if they did not have radiation shields, or a portion of them did not have radiation shields. Overall, though, we did get a 1:1 correlation for heat index. And since we are primarily interested in distribution, we kind of went ahead with it for that study. The other big issue for disparity studies is that the private weather stations have an income bias. Primarily richer people are buying the citizen weather stations and putting it in their backyard. So you're going to get a sampling bias if you use these for studying disparities. And there are other issues, like they're not really available in industrial or commercial areas, which tend to generally have higher urban heat island. The other big uncertainty with crowdsourced data, and this is not from the same kind of crowdsourced data, this is for mobile measurements, which are also increasingly commonly used for just measurement campaigns, as well as NOAA uses a bunch for their urban heat mapping campaigns. It's very difficult to get sufficient measurements from these campaigns to get climate scale signals. You're usually measuring during a single day. So that's like essentially a weather signal. And also, it's really hard to get enough sampling to cover the entire city. And there are like logistical constraints for that. So that brings us to models. So we kind of have to use models to try to get this spatial variability in a more continuous manner. And I'm going to talk primarily about mesoscale to Earth system scale models. And in terms of mesoscale models, there have been multiple kind of generations of Earth system mesoscale models. Initially, they didn't really have urban areas, but the first generation essentially had slab representation of urban, where a grid was given a different thermal or radiative property if it was urban. Then you have like one single layer canopy models, which have some morphological impacts on, say, the convection and wind flow included. Then you have multi-layer canopy. And the most recent, you have like multi-layer canopy with vegetation included. And from kind of the literature, the most common model used at the mesoscale for urban heat-related work is the weather research and forecasting model. And this is since 2000, this review, based on this review. And of these, the single-layer urban canopy model is the most common. So how do these models represent urban variability, intra-urban variability? There are like three main ways this is done. The first is based on density classes. So the urban grid can be either medium density, low density, or high density. And each of these density classes have different thermal, radiative, morphological properties. So all of your variability within the city is constrained by these three modes, which is really not a lot. More recently, people have started using local climate zones. This is similar in principle, but instead of 3 density classes, now you have 10 different density classes within urban areas, and then a bunch of like non-urban density classes. And here's an example for Chicago, where you can see. So the first one, for instance, this was Sydney, and this is for Chicago. And essentially, you can see a lot more variability within urban areas in terms of different density classes. The third way to do it is by having different fractions of urbanization for each grid. So you can have a grid be 90% vegetation, 10% urban, or 50% vegetation and 50% urban. However, here you're still using the same property for all of the urban grids. The assumption is all variability can be captured using the fraction. So here's an example from a different study I'm on, where they use NLCD-based urban fraction from 1980 to 2018. So we use this last method in this study to try to understand this disparity question. So we are basically running a single layer urban canopy with the urban density class over the US at 1 kilometer resolution. And we took the model outputs and then aggregated them to census tracts. We also did this for redlined HOLC grade, which I'm not showing here. But what we found was there were pervasive disparities in moist heat stress across US cities. And the way I'm showing this is these are the slopes from linear models between income and heat index as predicted by the model. And these are generally negative, which means the warmest parts of the cities have lower income, essentially, which is there's a disparity by income. Another interesting thing we found was that when you look across all of these cities, and we had like 481 urban clusters in the US in the study, we found that the degree of disparity given by the environmental concentration index was actually strongly associated with the degree of racial segregation. Here we are using a dissimilarity index between white and non-white populations within the city, which was a very interesting result. However, when we look at the magnitude of disparity, and here I'm showing the magnitude of the disparity as kind of the median of the slopes for all the 481 cities. Land surface temperature, skin temperature from the satellite, air temperature, relative humidity, heat index, and humidex. Humidex is another moist heat stress index. You can see that these sensitivities are much smaller for air temperature compared to, say, land surface temperature or skin temperature, which means that using satellites is generally going to overestimate your disparity compared to actual air temperature. One thing to note here is that the land surface temperature and skin temperature are different. And the reason is that they are conceptually same, but not really same. As I mentioned, land surface temperature is more of a directional view of whatever the satellite sees. So this can be partial roofs, partial walls, shadows, et cetera. In the model, the skin temperature is an actual integrated value for all of the urban facades as represented in the model. So it is somewhat different. Plus, there are many differences between the model and actual observations. So that brings us to Earth system models. Most Earth system models actually still do not have urban representation. And partly this is because urban land fraction is still pretty small, like less than 1% of the global land. So it's assumed that this won't impact broader climate. A few of them have the slab representation, and there are a couple of models, primarily the community Earth system model, and then E3SM, which is DOE's version of the community Earth system model, which has the single layer urban canopy representation. And this is what it looks like. You essentially have roof, you have walls, which can be sunlit or shaded, and then you have a canyon floor, which can be either pervious or impervious. And all variability within the city is given by these medium density, high density, and tall building district. It also has a low density class, but it's too vegetated, so it's not considered urban. So now, one thing with a global model is that you have to give it global surface properties, and these properties are not the same. The albedo of buildings in settlements which are not in the US have very different values than what you would expect in the US or in Europe. So what's E3SM and CESM does is that it divides the whole world into these 33 regions, and each of these regions have unique values for radiative, thermal, and morphological parameters. However, I mean, you're basically saying that the whole of China has one value, and China has climate zones. And if you have ever been to an arid city, they tend to be whiter, in terms of color than colder cities, because people know that white color reflects more radiation. So this is not reasonable. And when you look at observations, you can kind of see that. So both of these show the black sky albedo, which is the reflectivity of direct beam radiation from the sun, from rooftops, essentially. And you can see a lot more variability in the satellite observations compared to what the model gives us. And this means that we are going to be underestimating variability across cities if you use these parameters. And this is also a big issue if we want to evaluate the modeled values of surface temperature using satellite-derived surface temperature. And this is often done. So this is like MODIS-derived surface urban heat island versus, and this is a paper in Nature, by the way, and the community land model derived surface urban heat island. But if you look at the emissivity values, This is the emissivity for Aster. It's close to 0.96 for urban areas. And this is the emissivity prescribed in the model for, say, impervious road, pervious road, roof, and wall. These are huge differences. And if you think about like the Stefan-Boltzmann law, even if you captured the emitted long wave correctly, your emissivity is going to affect what is the surface temperature. So what we did was we looked at the observed surface urban heat island for very different emissivity models in satellites. And then we calculated kind of some conceptual surface urban heat island if we were to use the emissivity from CLM and WRF, and they're much higher. So it's not really reasonable to expect the surface urban heat island in a model where the emissivity is so wrong to be same as the observations. So I don't know why this works so well, because there are other issues with the models. So another big issue with the model is that there is no vegetation. So I showed a lot of pictures over New York, and you see different amounts of vegetation. But in the model, this pervious canyon is essentially treated like bare soil. So that's going to have a huge impact on your latent and sensible heat fluxes, and potentially also on airflow, temperature, and humidity. And vegetation is important. Here we can see how the monthly variability of the surface urban heat island is affected by the monthly variability of delta EVI, which is the urban-rural difference in enhanced vegetation index, which is another satellite-derived estimate of green vegetation. And we cannot just use vegetation in the surrounding background area as a proxy for urban vegetation, because urban areas can have very different vegetation, less or more depending on the background climate, very different seasonality. So you can have a change in the phenology of vegetation due to the urban microclimate. So you need to actually prescribe vegetation carefully within urban areas to accurately capture the overall urban climate signal. And not just the overall climate signal, the climate signal across neighborhoods. So this shows census block group level canopy cover for Los Angeles and San Francisco. And you can see large spatial variability across the cities. And interestingly, they are also associated with socioeconomic characteristics. Generally in the US, poorer neighborhoods will have less vegetation, less tree canopy than richer neighborhoods. So that brings us to this question. If we are not capturing this variability in surface properties, and the models are running at very coarse resolution, so these are like the typical resolution of an Earth system model, like 0.9 degree, does that mean that Earth system models cannot capture the intra-urban variability at all? And the answer is yes and no. So there are like two things that land models do to try to capture surface heterogeneity. Most global land models run with something called a subgrid structure. And this is important not just for urban cases, it's just important for any kind of land use transition. So if you want to look at what happens to grassland when it's converted into forests, what happens to agricultural land when it's laid bare, stuff like that. So all of the urban, or all of the land units are within each grid, and they're all running with the same atmospheric forcing, which means each urban land unit can give a unique response, and that's averaged up and sent back to the atmosphere model to the coupler. But that's not important because we can actually extract the values for each of the urban land cover classes. Similarly, we can extract, say, medium density class, tall building districts, and the low, high density classes. So you can get some level of variability, even though the actual atmosphere model is running at very coarse resolution. But the atmosphere model is running at very coarse resolution, and there is going to be spatial variability from that forcing data as well. And that's not really captured in the global models. So this is an example. We did some mesoscale scale simulations, 4 kilometer over Chicago, and you can see the lake to land gradient over coastal areas, and very different values for skin temperature, air temperature, wet bulb globe temperature, being another heat stress metric. And this kind of spatial variability across the coastline is not going to be captured in a global model. For instance, I'm showing here kind of two reanalysis data sets. The NCEP-NCAR reanalysis is kind of the older generation, 2.5 degree, like this is just very coarse. And ERA5 is, well, other than ERA5 land, which is a 9 kilometer, this is the finest resolution global reanalysis we have. And the actual climate models are still running at kind of this kind of resolution. And DAMET, of course, is 1 kilometer. So this is not enough to capture this kind of coastal heterogeneity. And note that DAMET does not really resolve urban areas, so it's not helping us with the urban issue. The other big issue with the when we think about the subgrid structure is that the model does not care where within the large grid the subgrid is. So the subgrid could be either right at the coast or inland, and it does not matter to the model, but it matters in real life. Another kind of thing I want to talk about here is that when we run the mesoscale models, there are other issues related to how the different model components interact with each other. So for that same study, we looked at different boundary layer schemes, the YSU and MYJ scheme. We use the NOAA land surface model, which is like a slab-based representation of urbanization. And then we did like a three-way nested 9-kilometer, 3-kilometer to like 1-kilometer resolution over Chicago versus 4-kilometer in the original simulations. So we do see consistent disparity in heat exposure during daytime for all the cases. They have different values, which is kind of expected. But then we look at nighttime, and it's kind of all over the place. And a lot of that has to do with how the different boundary layer schemes actually interact with the anthropogenic heat flux in the building energy model. NOAA, the slab-based model, does not have any anthropogenic heat flux. And this one, the nesting apparently also has a huge impact on the nighttime spatial variability. So going back to the other study from the disparities paper, we do capture the general direction of heat exposure within cities. So this is for Baltimore. We're looking at land surface temperature and heat index. And generally, it's giving what you would expect, that the urban core has higher values than the suburbs. And if you look at the range of values, the heat index has less range than land surface temperature, which is what we discussed earlier. And this is, of course, just the census data for per capita income. And if you look at race, you can kind of see like the Baltimore black butterfly. The problem is, while it's capturing the general direction of temperature, I wouldn't use it for actual neighborhood scale estimates, just because there are so many poor surface constraints at those grid scale. And just kind of bringing this up again, the urban fraction method is not foolproof either, because it's very hard to get what is a true urban fraction. I've been doing some recent work on this and trying to like compare very different land cover data sets and their urban representation. And they're kind of all over the place. So MODIS, for instance, shows very little change. And part of that has to do with how it defines urban as anything above 30% impervious. Then at the newest 10-meter resolution estimates of urbanization also show the largest variability, because some of them define urban as urban plus urban vegetation. Some define it as only settlement without roads. And then some define it somewhere in the middle. And kind of looking at this from the kind of present day estimates of urbanization. So here you have the MODIS land cover, which is kind of the default in something like WRF. This is the data set which is going to be in the next version of WRF for urban. This uses like 100-meter land local climate zone classification. And this Jackson et al. Data set is what's used in CLM, CESM and E3SM. And again, note that the low density is not actually used in the model. So there are large differences, and the global differences don't show just how large the variability can be at the local scale. I have an app for that, but I didn't link it to this presentation. And similarly, when we think about future urbanization scenarios, now there are a bunch of different ones from different research groups, and they are kind of all over the place as well. So there's going to be a lot of uncertainties when we try to project these urbanization scenarios to the future. So that brings us to some of the paths forward and some of the intermediate results. And this is something I'm doing as part of a recently funded DOE early career project. Is first, I'm moving away from these density classes and instead providing spatially continuous estimates of urban radiative, morphological, and thermodynamic parameters. And this is going to be done primarily using the most recent generation of satellite data, which are available at 10-meter resolution. And the other one is explicitly representing urban vegetation and its interactions with climate. So this is kind of a schematic of how like the pervious part of the urban canyon will now have like grasses and trees separately. And for each grid, we are also giving it like properties like leaf area index, height of trees. Species is harder because it's very hard to get that data, but you have to start somewhere. And I wanted to show some preliminary results. I talked about the issue with emissivity. And here we see like the emissivity as prescribed in the model for all of these different regions in the world. And then this is the emissivity from MODIS. And we incorporate that into the model, into basically this is done for CLM. And this is the original estimate of the surface urban heat island difference between CLM and MODIS. And then this is the value after we do the adjustment. So as you can see, in most places, you can see a reduction in this difference. And remember, I had hypothesized earlier that if you use a lower emissivity, you're going to overestimate the surface urban heat island, which is what we are seeing here. And this is improved once we adjust the emissivity. Of course, it's making things a little worse in other places because this is not the only issue. Similarly, for the other paper I'm talking about the disparities using the 1 kilometer resolution simulations over the US, I basically vectorized the surface data set used in the WRF simulations. And then I calculate the mean urban land surface temperature versus the WRF simulated skin temperature. And overall, it's working well. But then you look at the mean bias error, and it's like 5.6 Kelvin. And then we do this emissivity adjustment. This is done like post hoc. We are not rerunning the model. We are just like doing it by like the ratio of the emissivities essentially. And once you do that, the mean bias error goes down to like 1.5 Kelvin. So emissivity has a huge impact on the land surface temperature. And it's particularly an issue in urban areas because the urban emissivity prescribed is very low in these models. So that's like 1 kilometer estimates, which cannot really resolve the urban facades. So you have like in all of these models, you have buildings, you have roofs, particularly roads and walls. The way to do that is to leverage 10-meter resolution satellite data. So here, this is part of Seattle, and this is like the Space Needle. And this is the 10-meter resolution albedo product. It is almost global. And you can see that the whiter buildings, whiter roofs are showing up as higher albedo values, which makes sense. They're reflecting more radiation. And then you can actually make out some of the green spaces. You can make out roads, which are going to have lower albedo values. So now we have this 10-meter resolution urban, well, not urban, it's essentially everywhere, albedo data set. We can then combine that with building footprint data set. And there's a lot of available footprint data now, like Microsoft has one, Google just released one. And we can do this by kind of aggregating this for each 1 kilometer pixel and getting like an average roof albedo, average road albedo. Wall is trickier. We essentially just use ratios from the existing data set at this point. We'll figure something out later. And so we can get this 1 kilometer data set for the whole world. And it's already done. It's actually already done for all of these variables. So one of my collaborators at UIUC, his PhD student, Yifan Cheng, has been working on this. So I'm going to show some examples this is for Atlanta, Georgia. So in E3SM, you have the default roof fraction for medium density class is the same everywhere because the whole city is inside one of those 33 regions in the world. And then this is the default roof albedo. And now we have 1 kilometer updated roof fraction, updated roof albedo. And this can be incorporated, at least in E3SM, pretty easily because it already has a grid structure. I don't know how this would be directly incorporated into something like WRF, but the data set is not model specific because it just has anything for an urban canopy model. The other way we are looking at better resolving heterogeneity is running the Earth system models at much finer resolution. So I talked about like that 1 degree resolution stuff, but now there's something called high-res MIP where people are just running Earth system models at kilometer scale. And we are doing some of this work for a project called ICOM, and we call this, well, we're using this for many different projects, but it's called the regionally refined simple cloud resolving E3SM or SCREAM at 3.25 kilometer resolution. And at this resolution, you can start making out that different parts of the cities have some variability. This is showing relative humidity, like the urban core has the lowest relative humidity, and then it kind of increases as we move towards the suburbs. I mean, 3.25 kilometers is still really bad, but the plan, at least for my early career, is to eventually run 1 kilometer over the entire US coast. Hopefully, the computational capabilities will catch up by then. I mean, technically, there are people who have run it 1 kilometer, but for like 5 days or something globally. So I kind of wanted to now go to a different kind of model, and that is data-driven models. And the reason is that there are a lot of different working parts to fix in the process-based models to try to understand spatial variability. And I think there are stuff that are possible to fix and stuff that are going to be much harder to resolve as we move forward. Data-driven models are a little easier because we can just let data be our guide. So you essentially start with like in situ observations and you train the model. You use some of the same features. You use albedo, you use vegetation at like 10-meter resolution, and then you can get like spatially complete estimates of say air temperature, humidity, and this is like humidex. This is done for Chapel Hill for a study last year, and this is kind of related to stuff I will be doing for the NASA grant that Ken mentioned, and probably not going to go into this, but this shows like the different variables we included as features in this particular model. And this similar kind of machine learning models are also used by NOAA. So NOAA has these heat mapping campaigns where they essentially give sensors to community groups and researchers, and they kind of drive around or bike around. And then you have some measurements, train machine learning models using them, and get like more of a complete picture of the heat island over the city. The problem with all of these heat mapping campaigns is that you're only getting estimates for a single day for a very specific kind of surface. You are generally over roads, sidewalks. You're not really going into as much industrial areas. You're not going into people's houses as much. So the other way to do this is instead of using the mobile transects, you use fixed sensors. And a lot of these are available from the citizen weather stations. And we did something for Olympia, Washington, where we set up around 38-ish sensors. And the cyan color stars show the location of these sensors. And we had sensors give estimates for the whole summer. And then we did some similar machine learning estimates. So again, land surface temperature shows similar variability as maximum air temperature, but the range of values is like tiny compared to what land surface temperature is going to give you. These have different sampling biases because you're now no longer getting roads. So ideally, we want to combine both the fixed sensors and the mobile sensors. And that's kind of some of the plans from, and this covers both the early career as well as the NASA grant, is that trying to archive all of these different sensor networks now available. I already talked about the citizen weather station data available over Europe. We have a lot of data from personal weather stations from Weather Underground. I have a collaborator who like downloaded a bunch of them, like over 100,000 stations. Data is a mess, so someone has to work through that. And there are like existing urban meteorological networks. Even like Google Street View cars have air temperature, humidity measurements in them. And again, a lot of data to work with. So the idea is to kind of combine all of that to create an archive of observations that's going to be relevant not just for model improvement, benchmarking, and for model training. So, and other people are also doing it. Like there are folks kind of trying to archive all of the Netatmo observations, a lot of the Mesonet observations, and you can actually reach out to, well, I would reach out to Benjamin Bechtel, and he basically has a way to kind of share all of the data. And some concerns, I kind of talked about this earlier, but I will talk about this again, is the issue with the radiation shield. So whatever model you train using these observations may have some systematic bias that needs to be fixed. And I'm planning to do some work on trying to understand these biases, doing actual measurements after like 7 years. And the other issue is related to like the response time of some of these cheaper sensors. So if you compare with like research grade sensors, you can have very slow response times in like eye buttons or something, or sometimes higher response times depending on whether it's exposed to radiation or not. And that's particularly relevant if you want to capture a heat wave event. Okay, so one final thing before I stop. I talked a lot about like temperature and humidity and its spatial variability. But when we think about actual heat loading at the pedestrian scale, what really starts mattering is radiation. And I think, at least from the climate science, atmospheric science perspective, we don't talk as much about radiation within urban canopies. I have a collaborator who runs like radiative transfer models where you can get like 1 meter resolution estimates of mean radiant temperature, or UTCI. And there are other people doing this as well. And you can kind of see, and this is compared to like Landsat observations of land surface temperature. And this is the UTCI based measurement. So shading has a huge impact on the actual heat loading at the pedestrian scale. And this shading is not just due to vegetation. It can be due to buildings and other shading structures as well. These are very expensive to run. That's one issue. So, and these are at meter scale. So you have to save a lot of data. But these data, actually, these estimates are available for multiple large cities, including Baltimore. If anyone wants more information, I can put you in contact with him. And with that, I come to an end. And I think I made good time. But like summarizing, for various reasons, there are issues with the process-based models, especially when we are trying to understand the intra-urban variability. And I am not trying to fix all issues through my projects because I don't have the expertise to do that. My focus is to try to constrain what we can constrain, and that is urban vegetation and the surface properties and their spatial variability. Once we do that, we'll probably still have issues with the model, and then we can think further in terms of what we need to do. And note that these surface constraints that we are developing can also be useful features for training data-driven models, which I think are pretty good from the prediction perspective, but may not be as helpful for generating fundamental scientific insights. Thank you for your time. And kind of thanks to so many collaborators on so many different projects and papers that led to all of these results. If you have any questions, let me know. You can also contact me here.
Plenty of time for questions. I'm going to open up the online view here in case anybody has a question online or you want to put something in the chat, feel free. Maybe give the online folks first dibs. There's a big crowd. All right, not hearing anything online immediately, so let's go to the room. Any questions for TC? We're all quiet after break. Here we go.
I have a question.
Oh, okay. We'll give Chris online the first shot.
Okay. I was really intrigued by what you were doing with the handling of the radiative transfer in the cities, and I was wondering what's the status of the angle issues in terms of getting the shadows on the cities that you're
Thanks.
here.
So this is done for different times of the day. So it does include the position of the sun. So we are getting essentially different values for different hours. And ultimately, we do want to know what's happening with the shadows, right? Like the shadows are what's reducing the radiative loading at the pedestrian scale. Does that answer your question?
Yes, I think it does. It's essentially getting the angles correct and getting the shades properly done.
Right.
Okay. Thank you for that. Yeah.
So I had a question on incorporating vegetation into the radiation models. How is that done exactly? Is it they're not explicitly represented in one place? It's just kind of a parameterized sort of thing?
Yeah. So I don't know about all models.
Yeah.
The way it's done in like WRF BEP3 is it does a Monte Carlo approach with like different possible radiation paths and tries to understand how much of that is going to be blocked by the tree. And then you kind of average that up to the whole grid. There are other ways to do it. And I have kind of thought about it more of as a scenario approach. Like you assume within the urban canyon, I mean, it doesn't make much sense in my head to say like it's going to be shaded under the tree. People know that. It's not profound. But you can get estimates for what would be the typical heat loading if you were under complete shade, if you were completely sun exposed, Or if you were partially shade in that, you can look at diffuse radiation, for instance. So that's not going to be directly blocked by sunlight. So you give that scenario approach and show like how large of a difference that can make, rather than actually trying to estimate. You can estimate, again, either you solve the entire 3D radiative transfer equation, which is very expensive, or you do like a statistical method, statistical kind of approach to do that. But I don't know if it's particularly profound to tell people that, if you're in shade, you're going to absorb less radiation.
Yeah. Because I was thinking about like canopy radiation schemes in general. I mean, it's kind of a very complex problem and an ongoing question. So I just wasn't sure how you guys were planning to incorporate it.
Yeah, so
like that.
there are a lot of uncertainties there, and I am not the expert on that. I will get a postdoc who is an expert on that to do that. So I will let you know once he joins.
We just have one more question there. I'll note I can't see the chat. And so if anybody online sees the chat and there's questions in there, please speak up. But next, I'm going to give this to Ben.
Thanks for the nice talk. I have a kind of a big picture question. As I've developed into this like urban modeling and urban observation, urban climate space, I've noticed almost every modeling talk or whatever that I've seen is just essentially said the models that have existed in the past are not high enough resolution. We don't have enough data. It doesn't resolve properly the various mechanisms that occur. That of course makes sense in an urban area that's like highly heterogeneous and small, on a globally spatial scale. But as we go higher and higher resolution, as you pointed out, it gets more and more complex to run. It gets more and more expensive to run. It gets more and more unwieldy in terms of practical.
Right.
What are your thoughts on balancing the need for higher complexity and higher resolution with actual usefulness and uncertainty?
Yeah, so it depends on what your approach is, why you want to improve the models, right? So I think BSAC probably wants to improve models to actually have that be applied, versus like my early career is actually focused on just improving the model. It doesn't have the goal of having it be applied directly. It's just there is a scientific gap. We are filling that by improving the model. And note that I talked about the subgrid structure, right? So the main computational expense comes from the atmosphere model. So in theory, you could do pretty high resolution urban heterogeneity, like conceptual urban heterogeneity. So you can say like, this is the distribution of temperature within cities without having to actually run the atmosphere model at very high resolution. You will have issues like in the coastal areas where you're not capturing the atmospheric forcing, but there are ways around that. And I don't think all of that has to do with the actual resolution of the model itself. Some of that has to do with the surface constraints not having the resolution. So even with finer models, say 1 kilometer WRF, if you're giving the same surface constraint for the entire city, that's not an issue with your model resolution. That's an issue with your data set resolution. And that can be fixed without actually changing the computational cost at all. So.
Two more questions here.
Thanks for a really interesting talk. I'm a geologist, so I don't, I understood your talk and I thought it was interesting, but I don't always understand like why you're going to do something. And I also have a class of undergrads here who maybe this is the first thing we're going to talk about on Wednesday is like at the highest level, why are you doing this? I do understand what you're trying to do, but why are you doing it? You just want a better climate and weather model? Or, do you want to understand something about racial disparities or, at the very highest level, why are you doing what you're doing in this talk?
Yeah, I think at the highest level, I want to know why models are not performing well and how we can do to fix it. That's my kind of overall goal, like at least for one of the projects. Well, urban scale processes. I'm focused on urban areas. And even like for weather and climate, it really depends on the scale you're looking at, right? But that's a whole other field that I'm not really in. For the specific project, yes, we want to better estimate heat-related disparities, not just like climatic conditions, but also under extremes. And having a process-based model allows us to gain mechanistic insights that are helpful beyond just doing it using observations. So I think for me, it's more of overall, it's a fundamental question of better understanding the system with potential applications, which is how I'm funded, at least for one project.
First off, I really enjoyed your talk. And I know when you were talking about the current gaps, you spoke on the income bias that happened with predominantly, it looked like European countries, which would be mostly first world. And I'm just curious on if the data sets then for, say, like third world countries is then like lacking. How do you incorporate that into your model set?
So that study itself is not focused on non-US cities, but I am doing some work on cities in the global south. Interestingly, there is actually no real outdoor disparity in heat exposure in a lot of global south cities. And this is why I was very surprised when I came to the US and did that study on disparities in US cities. US cities are structured very differently than most cities in Asia, in Africa. And a lot of that has to do with, you know, a lack of public transit, car reliance. So you have heard of like white flight, urban flight, where like richer populations move to the suburbs. And suburbs are generally going to be cooler than the urban core. There's also like the history of redlining, where a lot of the urban cores were basically redlined so that the mortgage lending was much harder to get. And that led to like systematic lack of investment in these neighborhoods, which kind of we still see to this day. Cities in a lot of global south are very different. People like living in the cities. So like richer people will live in the urban core, even if you have the highest temperature, even if you have the highest pollution. It doesn't matter as much because you have air conditioning. You're not really exposed to the outdoors. So that was very interesting to me when I saw like the results here for US cities. And I'm currently doing a study looking at this cities in the global south. And the reason I'm doing it is because there has been kind of a traditional kind of paradigm of people taking results from Western studies and then like saying this is the norm, when that's not necessarily.
There's a question online in the chat.
Oh, I cannot see the chat.
It's from Troy Bernier, and it says, have you looked at using water vapor isotopes for land use partitioning?
No, I have not. My advisor used to do that, my PhD advisor, but I have not done any kind of observations for like 7 years. So
Okay.
Great. Thank you. My question is regarding the surface emissivity. So you talk us satellite emissivity is the higher than your surface the surface measurement, right? If then currently satellite emissivity, they have some threshold to use their data, or they reflect some correction factors when they use the satellite information.
So there are like many different ways to get emissivity from satellites. So if you look at the MODIS land surface temperature, like the A1 product, they use that's another whole thing where they use a land cover based emissivity classification system. So each land cover is prescribed an emissivity, very similar to what the models do. However, something like Landsat is using a vegetation adjusted emissivity based on another satellite called Aster. So Aster's advantage is it has 6 or 7 different thermal bands. So if you have 7 different thermal bands which have different emissivity values and essentially different thermal radiation values, you can iteratively solve for land surface temperature. You cannot analytically solve it because the system of equations is not closed, but you can iteratively solve it. But I am not actually saying that the emissivity from satellites is correct, because a lot of the empirical models that we use for satellites are not urban specific. What I'm saying is that you cannot use satellite derived emissivity based LST to evaluate modeled LST because of the emissivity. So it's a question of like how they're used in practice rather than what is the truth. I think truth is a bit tougher to get because we actually need urban scale emissivity estimates, which really don't have that much.
Gonna walk this microphone over to your next question.
Not so much a question anymore because you actually sort of answered it when you're answering another question. But I was thinking when you showed the map of some of the observations, I think it was over Europe. It makes me think about the areas.
Um,
m-
are you talking
forget
about the citizen weather station one or?
Yeah, some of the citizen, yeah, mainly looking at the distribution of like the observations.
Right.
But especially since you've been looking at this at the more of a global level, some cities that may have like that have interesting topography, yes, that figure. There's probably you can cherry pick some locations where the variability may be dominated just by the topography and where you have, and I'm just kind of wondering how that really kind of imposes
Yeah.
onto our health metrics.
So this topography issue is both a concern when we're doing satellite remote sensing. The standard is to take some threshold. So we take the mean value of the city, like the mean elevation of the city, and then remove certain pixels if they're like more than 50 meters, up or down. I mean, there's no clear threshold, like people use that. For the citizen weather station data, there have been a lot of work on quality control methods. So one of the thresholds they use is based on the height compared to like nearby stations. So they take the whole sensor network, then calculate the height of the sensor based on some digital elevation model, and then remove certain sensors if they're like have a huge they're a huge outlier from the surroundings. So there are ways to do it, but it's not perfect because you're dealing with like hundreds of stations. So you're going to have some which kind of slip through, and maybe some of the assumptions when we deal with the quality control methods are also not correct. That's a whole other thing I have where people will do outlier detection for urban stations based on nearby rural stations. The problem is that we don't expect the distribution of temperature in urban stations to be identical to rural stations. So why? That's a whole other thing. And I don't have a good answer to it at this point.
Thank you.
Any additional questions?
I have one more question.
Go for it.
So you put up a description of the daytime boundary layer, and it did pretty well in terms of modeling it. But when you went to the nighttime, it really failed. So are there groups that are working on that problem, or is it a kind of a lost issue?
So one of the reasons, one of the big reasons people move to multi-layer canopy schemes in urban areas, or sorry, just single-layer canopy schemes, was because the slab models were very bad at predicting nighttime urban heat island. It used to be like mainly the anthropogenic heat flux issue, like it was not incorporated appropriately. So is a big problem that is, people are trying to solve. But the question is always like, how do you solve it? Because there are multiple ways to get at it, right? As I mentioned, the constraints in the model are already wrong. That particular simulation, for instance, did not have vegetation in it either. So there's another validation that we did where we looked at satellite. We did look at satellite area of surface temperature after like adjustment versus the gridded skin temperature from the model, and looked at the bias as a function of vegetation, and it was very strong. So because the vegetation is not being captured in the model, that's affecting the variability. So once you include vegetation, that changes a lot of things. That changes your overall rough, the average kind of roughness length for the whole grid. That changes your sensible heat flux, latent heat flux. So it's, I can talk about what could be wrong, but there may be multiple different things that are wrong, and you might fix one of them, but because another thing is wrong, it looks good now. So that's why I want to focus on stuff that can be fixed first, like for which we have some observational constraints, and then see how bad the models still are.
And can I follow up with a question about the data that you would use in order to test the nighttime?
The what? Sorry, can you?
What data would you use to test the nighttime performance?
So that was not for boundary layer height, by the way. That was just for air temperature. I was looking at, so we do have, so that was for Chicago, right? So we do have observations. again, for the other Chicago IFL, they have set up a lot of observations over the city. So you, in theory, have a lot of spatial heterogeneity in observations that you can use for validation. So not all cities have that, but Chicago is one of the few cities where you do have some possibility of validation.
Thank you.
All right, let's thank TC again. Nice discussion. Thanks for all the good questions. See you all in
Thanks
a
for
week.
coming, everyone.